So in this subtopic, we are going to have a look at the polarity of the molecules. Okay, so before we do that, let's have a look at the bond polarity. The bond polarity exists when two bonded atoms unequally share the electrons, resulting in a negative and a positive terminals. So basically, if the atoms got different electronegativity, it has a polar bond. But if the electronegativities between the atoms are the same, it is a non-polar bond. So the polar bond, okay, is shown by using a polar arrow. Okay, so for example, if we have the hydrogen fluoride, so hydrogen fluoride got two different atoms, so obviously it has a difference in electronegativity where fluorine is more electronegative than hydrogen. So fluorine is the negative terminal, hydrogen is the positive terminal. So we use the polar arrow, okay, where the head of the arrow will goes to the more electronegative atom, and then at the back here, like a positive sign, will goes to the more electropositive atom. If you look at these two, okay, the polar arrow for the hydrogen fluoride is shorter than the hydrogen fluoride. Okay, why? Because fluorine is more electronegative than chlorine. Obviously, okay, the difference in electronegativity between hydrogen and fluorine are bigger than hydrogen and chlorine. Okay, for fluorine and chlorine molecules, okay, these two atoms are the same. So obviously there is no difference in electronegativity. So the electronegativity are the same. So that's why these two are a nonpolar bond. For a simple diatomic molecule such as the hydrogen and fluorine here, okay, so we can determine its polarity of the molecules just by have a look at its bond polarity. So the bond polarity between these two atoms are polar. It makes this molecule polar. But then for a larger molecules, which is the molecules that have more than one covalent bond, okay, we are going to determine its polarity by have a look at its molecular shape and also its bond polarity. So the dipole moment is used to measure the molecular polarity quantitatively by using this formula. Q is the charge, R is the radius between the atoms. So the SI unit is coulomb meter, but the common unit used is dBi. So 1 dBi is equals to 3.36 times 10 to the power of minus 30 coulomb meter. But don't panic, we are not going to use this formula at all. As I mentioned before, okay, the polarity of the molecules for a larger molecules is determined by using its molecular shape and also its bond polarity. Okay, so I divide it into three parts. Okay, first have a look at the basic shape molecules, which is the AX2, the linear, AX3 trigonal planar, AX4 tetrahedral, AX5 trigonal bipyramidal, and AX6 the octahedral. So here I use the carbon dioxide, okay, as an example. Okay, so if the basic shape molecules got same surrounding atoms, okay, like carbon dioxide, the surrounding atoms are oxygen. Okay, the molecular shape, we know that it is linear. So this shape actually is symmetrical because we got two same atoms here. Okay, so even though the bond between carbon and oxygen are polar, okay, so where oxygen is more electronegative than carbon, okay, both are polar, but then the bond dipoles cancel out each other because of these two same surrounding atoms. Okay, so the resultant dipole moment is not is equals to 0. Okay, thus the CO2 is a nonpolar molecule. But then if I change one of the oxygen here into sulfur, such as so this is a carbonyl sulfide. Okay, so again the CO bond, okay, are polar, where oxygen is more electronegative than carbon, okay, and the CS bond is also polar. Okay, so sulfur is more electronegative than carbon, but then you can see here, since oxygen is more electronegative than carbon, okay, so the polar arrow for the CO, okay, so the difference in electronegativity between oxygen and carbon are bigger than carbon and sulfur. So this will make the bond dipoles does not cancel out each other, and we have a resultant dipole moment, okay, which is not equals to zero. It will goes to oxygen. Okay, so the carbonyl sulfide is a polar molecule. Next, let's have a look at the molecules with lone pair. So we are going to have a look at the AX2E, the V shape, AX3E, trigonal pyramidal, AX2E2, again the V shape, AX4E, seesaw, AX3E2, the T shape, AX5E, the square pyramidal. Okay, these six shape, okay, are will give you a polar molecules. Why? Okay, for example, if I take ammonia here, okay, so hydrogen and nitrogen, the bond are polar. Okay, nitrogen is more electronegative than hydrogen, right? And then the bond dipoles does not cancel each other because of the shape. Okay, so we have a lone pair here, so we can see that the resultant dipole moment will go up. Okay, so ammonia is a polar molecule, so the resultant dipole moment is not equals to zero because the bond dipole does not cancel out each other. And last but not least, for molecules with lone pair, which is AX2E3, the linear, AX4E2, the square planar. If the atoms got same surrounding atoms, okay, such as the ICl2 minus, okay, so the negative charge is on iodine, okay, so we know that the shape is linear, and because of the surrounding atoms are the same, it is symmetrical, even though the ICl bond are polar. Okay, so Cl is more electronegative than iodine. Okay, so it will make the bond dipoles cancel out each other. The resultant dipole moment is equals to zero. There is no resultant at all. So the ICl2 minus is a non-polar molecule. Okay, for the IClF minus, okay, so I change one of the chlorine here into fluorine. Okay, so again the negative charge is on iodine, so there is a difference in electronegativity between iodine and chlorine. Okay, so also between iodine and fluorine, but then the difference in electronegativity between iodine and fluorine are bigger than iodine and chlorine because fluorine is more electronegative, so it will make the resultant dipole moment will goes to fluorine. Okay, so the resultant dipole moment does not equals to zero, so the IClF minus is a polar molecule. So that's it.